Good morning, everyone. My name is Sujay, and I am the co-founder of this company called Viga Studios. So we've been in the business of VR and AR for over 3 years now. And apart from VR and AR, we also work on technologies to help the content creators. So over the last 2.5 years, for me, it's been like an amazing journey working on some of the cool projects in the space of education, energy, industry, and media content creation. So so what are we here for today, you ask? So I'm here to present a breakdown of one of the projects that we did. So the project was about simulating nuclear reactor scenarios in a cave environment. This talk is mainly focused for anyone who's starting, getting started with Unity, and getting started with using Unity for uh, industrial applications as such, and also anyone who are trying to understand what can Unity solve for their industrial use case. So moving on, to add a bit of a context, I have a small video of the project, that will, you know, give you what the whole project was about and give you a quick overview of the project. So this was like a quick glimpse of the whole project that we did for this particular client. So it was, the purpose of this project was to, demonstrate the failure cases of the nuclear reactor and the contingency measures they would take uh, inside the nuclear reactor. So the whole purpose of the video of the whole project was to educate the people who are working there, as well as to demonstrate the contingency measures they would take to anyone who's visiting the nuclear reactor. So first, let's understand what was the uh, whole setup looked like for the demonstration. So it's something called cave setup. So cave stands for cave automatic virtual environment. It's a recursive acronym, and basically, if you want me to describe cave, it's basically you walk into a room and you have all the walls being projected with the virtual scene. So as you can see in the picture there, it's like you have the walls, all the walls around you being projected with the virtual scene. So this gives a sense of immersion within the scene, as well as there is tracking hardware wherein your position and your orientation will be tracked, and you'll have a handheld input device with which you can interact with the scene as well. So this way you would have, this is like a different way of visualizing VR, not the traditional way of VR that we are used to with the head-mounted display and stuff like that. So this is a different way of visualizing VR. Apart from that, if the scene is stereoscopic, we can have like a 3D glasses with which the user can get a real 3D perspective of the scene as well. So with which we choose Unity for the development of this project, and to support to get Unity working with the environment, we need to have a plugin, and that's why Unicave plugin came in. Unicave is a project that completely aims at building a plugin for Unity, wherein they can speed up the workflow of uh, building cave environment projects much simpler. So that's the whole purpose of Cave plugin, and it's a really good plugin if you are getting started with Cave projects. And the setup that we were using was like a 4-camera setup. Basically, the left wall, right wall, front wall, and the floor. So these 4 walls were being projected with the image. So this is like a 4-camera setup, and each of the wall had like 2 cameras, one for the left eye, one for the right eye, because the whole this thing was stereoscopic setup. As a result, we had like overall 8 cameras within Unity that were projecting onto the environment. So moving on to the development pipeline itself, it's a very generic pipeline. So we get the assets modeled and we get them into Unity for building up the gameplay and behavior. And then once that is done, we deploy it into the actual site and test it there. So this is like a very generic pipeline that we followed. But within the development itself, if we break down the development cycles into modeling section and the programming section, so this is a chart that describes our pipeline for uh, getting the assets done. So we used Jira for our project management. We split down the tasks into into different tasks, and providing the task, each task with the proper description and references. We moved that, we passed it on to a 3D artists. So some of the 3D artists were working remote for us, so we had to get them on a VPN to to have them in our organizational network. So we had a internal database We are calling it Arsenal at this point. It's basically our internal database that we use for storing all the 3D models that are made for our projects. So this just makes a pipeline very very seamless, and it just fits into what we want. So we have it's been project under works right now, and it's been evolving project by project. And this was the first project we used Arsenal for in a production line. So once we get the artists to submit their models into Arsenal, we review them, and we we then get them onto Unity. So if at all we have any changes requested, we just communicate the same to the artists, and get the process running up. So Arsenal is one thing that simplified our workflow, and made the pipeline a bit smoother. And when it comes to the development pipeline for the Unity itself, so we had two teams working, one in Bangalore at our office at Viga Studios, and the other was a remote team that was working on site in the cave environment. So at Viga Studios, we built the entire scene, and we had a internal server for version controlling. We used Perforce for version control, and we had that server set up in-house at Viga Studios. So whenever there was a new change request or feature request that used to come to us, so we would we'd pull the latest changes from Perforce, implement them on the on our local workstation, and then submit the change onto Perforce. And once the changes are done, the remote team would pull the same changes there, build it for the cave environment, and just test it out there. So if at all they find any issues, they would flag the issues to us. If at all there are any minor fixes, they would do it themselves, and submit the changes back to Perforce. Otherwise, if at all there are any major changes, they would come back to us and ask us to fix it. So this was the whole pipeline that we followed for the inside the Unity part. And using Perforce, the major advantage was, Perforce has a very good integration with Unity. And having like large binary files and large asset files, Perforce Perforce made a lot more sense than using other version control systems. And then moving on to the scene development, it's like we had to build the entire environment from scratch. So we didn't really get any models from them. So we had to we need to figure out, visualize the entire, we need to take references from the nuclear reactors, real sites, and we had to build the nuclear reactor. And yeah, it came up to 7.5 million polygons to build everything. So all the geometry had to be modeled. A lot of LODs were to be made. So and then yeah, then they had to be placed in the right locations. And yeah, and some of the environment involved building, having water, and some of the props required them to be having smoke. So we used certain plugins within Asset Store, and apart from that, we took advantage of Unity's particle system to simulate some of these kind of props, I'd say. So when it comes to materials, Unity's PBR material is a really good thing. So what we just need to have the right texture maps and to play around with the materials to get them right. So we mostly used Unity standard shaders, and we made our custom shader for some of the props. And apart from that, there is one more shader pack called Uber shader pack, which we used occasionally, but then not too much. So this just gives the difference between having a simple textured asset, and then having an asset with normal and bump maps, proper normal and bump maps. So it makes a lot of difference from the looks point of view. And yeah, it's important to have them in the pipeline. So same thing here, but you can see the difference between having a simple texture and having a prop with all the normal and bump maps assigned to it. So when it comes to lighting, it's really important because it's a major aspect in two things. One is the look of the whole scene, and the other is the performance of the whole project. Because lighting sometimes is seem to be very performance intensive calculation when it comes to gaming, and at the same time it's again something that contributes a lot to the look. So it's not like we can have a lot of lighting in the scene and get away with the performance. We always have to do a lot of faking in the lighting when it comes to building such scenes. So in our particular application, we use a combination of both baked and real-time lighting, just because we could real-time lighting because we could afford we could afford real-time lighting in with the hardware that we were using. So yeah, we took advantage of both the lighting modules. So exterior lighting, the scene, if you noted in the video earlier that I played, so there was like a large terrain with a lot of rooms and buildings that are uh, a large nuclear reactor site basically. So we ended up using real-time lighting because baking was taking huge amount of time for us, and we couldn't afford so much of time in the development cycles. So what we did was we ended up using real-time lighting, one directional light, and lit the entire scene with environmental lighting and ambient lighting. So the environmental reflections from the skybox makes a huge difference. So that was enough for us to light the entire exterior scene. So and the major reason to skip the baking was, it was very time consuming for a large terrain. So we had to stick to, using real time. And for the interiors, when it comes to interiors, the global illumination and the look was really important for us. So we used backlights inside interiors, but some of the props, such as the water that you see there, the fluids that you see there, and the caustics in the water, uh, they they required to have at least one real-time light. So we ended up using a couple of real-time lights in each of the interior modules. But then, yeah, that there were not too many of them. So again, like the interiors were mostly with the baked lighting because the global illumination, the looks were really important. So we had to stick to the uh, global illumination and a baked lighting pipeline, and we had to fake certain things with real-time lighting. And in terms of lighting, so we used Enlighten for big GI, and we ended up using low resolution light map settings for the development purposes. And once the setup was all up, and we were happy with the looks, we bumped up the resolution of the texture maps, and we baked it for during the final stages of the project. So this saved a lot of time for us. There's a very beautifully written blog post with Unity explaining the different settings that you can use to save the time. So if you're interested, just have a look at that. And and one more trick that we played in lighting was disabling the real-time lights. So basically, the trick was this. So whenever the user was inside whenever the player was inside the interiors of the experience, so we disable the real-time lights that were used in the exteriors, and the vice versa. Whenever the user was in exteriors, we disable the real-time lights that were placed inside. So this was actually a major boost for us in terms of performance. The FPS, bumped up a lot when we did this. A simple trick, but it was really effective for us. And when it comes to programming the behavior, we ended up using event systems, classes, and coroutines. I mean, the entire programming stack of Unity is based on that. So we ended up using that. And the whole idea was to have like a scalable and flexible architecture, and it should be performant efficient as well. So we ended up using event systems for handling the inputs and the custom timed events within the experience, and classes to maintain the modularity of the whole program, and coroutines to handle the sequence of events when and where they should happen. So it was really important for us to make a design choice of the architecture that we're going to use early in the project, because we didn't want to end up hard coding a lot of stuff and then redoing the same thing over and over again every time a new module is required. So we ended up creating an architecture like this. So the whole thing was, we had an event system which was like monitoring everything, and it was handling three major things. One was spawn manager, the reactor manager, and the timeline user interface. So the nuclear reactor event system also handled the inputs that were coming from either from the workstations that when we were developing, or with a flip switch, um, it would take the inputs from the cave environment. So just made the workflow a bit more smoother when we had to switch the environment from our workstation to a cave environment. So the spawn manager would be responsible for where the player would be spawned, whether it's the exteriors or one of the interior modules that we implemented. And apart from that, we had the reactor manager. So the whole purpose of the reactor manager was to control the behavior of the whole reactor system, and time the events properly, and handle each and every module that's out there. So all the whole scene was implemented in a one scene, and there were like different modules running parallelly. So the user could switch from one place to another place, and see what's happening in both the modules at the same time. So, and the each module that we implemented were, it was a scalable architecture, and whenever the client wanted a new module to be implemented or a new set of features, it was like very easy for us to go and add a bunch of code there and get the system working. So this was really important choice that we had to make early in the development, because otherwise we would end up in an architecture where we had to hard code a lot of things. So the user interface were tied very close to the particular module. For example, there was a user interface uh, that was indicating the temperature uh, of the reactor core. So those modules were tied together. So as a result, they're not like completely separated and isolated. So they were like integrated closely and coupled closely, and the behavior is directly reflected with the user interface. And when it comes to post-processing, we tried a bunch of things here. So the thing was, post-processing, one profile doesn't fit everything. So we ended up creating multiple profiles for each of the module. So for interiors, a separate post-processing profile, and for exteriors, a separate post-processing profile, and for likewise for the different modules. So the way we handled this was, whenever the player was spawning in a different locations, right? So we just had to tell the spawn manager to manage the player's post-processing stack as well. So it's just that the spawn manager would anyways keep track of where the player is being spawned. At the same time, it would just assign the material, assign the proper post-processing profile to the camera, and be done with it. So that way, the spawn manager was handling a couple of other things as well. So HUD was really important, because like that's something that communicates the entire status of the plan. So this was like the concept that we had for the HUD. And yeah, I would talk about a couple of important modules in the HUD as well. So facility map, this is like any mini map that we have on the first person shooter games. So you get to see where the player is at the moment. And also we ended up having a couple of indicators on the mini map itself, to handle to just indicate what's happening with different modules in the system. So the way this was implemented was having an orthographic camera looking down from the top, and we use culling masks to render out only the required game objects into the thing. So the play was real time, tracked in real time, and the facility map would get updated in real time. And the status panel, we needed a GIF animation to to communicate what's happening with the reactor core. Uh, but unfortunately, Unity doesn't support GIF animations, so we had to use a workaround. The workaround was to get a sequence of PNG images and then play around them in a fixed update loop. So that way, it was efficient, because we had a lot of control on when to stop the loop and when to continue. So it was a good workaround. And apart from that, we had to cut a lot of corners, and to implement some of the things and to speed up the development. So I would talk about few of them here. So one of that was building out these transmission lines here. So transmission lines in the scene, they were far out in the space, and we didn't have like a lot of we didn't want to spend a lot of geometry on modeling these on these transmission lines, because they were like far away from the user, and they just didn't need that much of detailing in the asset phase. So what we ended up doing was, we created an asset like that, which was like hardly had like 200 polygons, and then we used a custom shader, so which basically clips out any pixel that's not in the all the black portion was rendered transparent, and all the white portion was rendered as the transmission line. So this was like a simple trick that we ended up using, rather than modeling the entire transmission line. So this saved a lot of time in the modeling process. And one more issue was backface culling. Halfway through the project, what happened was, the clients wanted us to model a few more modules within the nuclear reactor site, so which was not the part of the plan in the early stages. So one of the thing was this dome itself. So if you look at this, the dome was not modeled with any thickness as such. So if you go inside the dome, the camera wouldn't render out the dome itself. So we didn't have like the thickness or the interior face modeled. So instead of sending dome for remodeling from the artists, we ended up using a different trick. So what we did was we used a procedurally generated interface. The way we did this was take the outer face, generate the outer face again, and just flip the normals to the exact opposite side. So this way we would get an internal face, and when we overlap both of them, we get an asset like this. We get a game object like this with both the faces. So this was one more trick that saved a lot of time for us, because like sending the asset in the production to the modeling and then getting it back would mean like we are spending a lot of time on iterations. So pipes were another tricky challenge, because like the requirements kept changing throughout the project. Like you just had to move a little bit there, connect this module to there. So they kept coming. So as a result, we had to find a flexible way of dealing with pipes. Sending the pipes to modeling and again getting it back is again a lot of iteration process. So we ended up using procedural content generation for pipes. So the idea was this. So we started creating our own plugin for pipes. So the way this works was we created a set of spline points, and based on that, a pipe gets generated. And in real time, we could tweak the uh, translation, rotation, scaling of the spline point, and that way we'd end up creating like any sort of pipe that we want. So once the pipe was ready, what we do is we'd simply bake the pipe into a game asset, and just integrate it wherever we want. So this way, we would like we had a flexibility even with the piping system as well. So yeah, you can do we ended up doing like a lot of things, like the smoothness, the radius. We played with a lot of things to get the efficient way of piping into the Unity. So one more place where we ended up procedural content generation for pipes was this particular animation. Instead of again, the position of that red vehicle kept changing. As a result, we didn't want to use an animated pipe to be modeled in Maya or something. So because of that, we modified that plugin a little bit, and to do this in a procedural way. So this was how the spline points were arranged for that particular animation. So we had these arranged, and whenever if at all there was a change required, we just had to move those points to a different location, and we had like a procedurally animated pipe ready for us. And for water simulation, we ended up using a lot of plugins from Unity Asset Store. So these were like really good plugins that solved the issues for us. And yeah, and end of the project, what we wanted to do was we didn't really have uh, you know uh, we didn't really have the want to showcase this in if you want to demonstrate this project to someone else. We didn't really have the case setup in our office, so we wanted to port this to a mobile phone. So the way we ended up doing this was capturing the 360-degree captures of the entire sequence, and then we ended up creating a video using FFmpeg. So that way we had a 8K video, and if at all we want to use it for a low resolution, low end phones, we would simply had to run it through FFmpeg and reduce the resolution of the video. And that way we ended up creating a mobile application that would run on most of the devices. Otherwise, if we had to render out the uh, whole experience in a mobile application, it would mean that we would only be targeting a very fixed number of devices. But now with this approach, we could target almost all the devices that support VR. So with that, I conclude my talk. I have like a few minutes to take the questions.
Any
If at all any.
questions?
How did you handle the floor in the cave setup?
The floor.
Yeah, you're
So
talking about the cave setup, the camera setup.
yeah.
So how do you project on the floor with the human
Okay.
being
Okay.
present?
So the
Yeah.
thing is like, I'll go back to the slide. So there are like different setups of the cave. The one that we used was we only had the floor rendered in front of the user, not the entire floor.
Oh, okay.
Yeah. So that way we had the user was not occluding the projector, and the floor was rendered directly from the top.
Oh, and did you also similarly handle the roof, or you left it out?
Roof was not at all not the
Not
part of
in
the
the
plan.
part of the.
Yeah. So we had like a 4 camera setup, that is left, right, front, and
Mhm.
floor.
Okay, and how do you think, what is the value proposition is compared to a headset? Because headset could have given all this in a
Right.
much better way.
Right. So the whole the I would say like there are like certain advantages for cave setup than with the
Mm-hmm.
VR headset. The thing is with cave setup you can have like multiple users experience the same thing at the same time. So there was one instructor who'd be walking them through the entire setup, and there'll be people with wearing 3D glasses, and they'll all be experiencing the same thing at the same time.
Mm-hmm.
So that is one huge advantage. And when you want to provide when you want to do the same thing with the HMD, right? So that would mean that you need to have 20 or 20 hardware setups, 20 Oculus or HTC Vive
Mm-hmm.
setups.
Mm-hmm.
So that's a huge thing. So
Okay.
that is a major advantage. And again, this the one more major advantage would be to these systems wouldn't give you any of the motion sickness and nausea kind of effects.
Issue.
Yeah,
Okay, but you can't interact with the environment
we can
in
interact with
this.
the environment. So the instructor would have a motion controller or an input device with
Okay.
which he could interact with the environment.
Okay, he's the one who's
Yes, yes,
connected. Okay,
yeah.
thank you.
Thank you.
So thank you so much for the sharing.
Yeah,
Right. If you have further question, I think Sujay is going to be
yeah,
by the side of the hall. Right.
sure. So yeah, I think I hope this you guys found this talk useful, and yeah, thank you.